Now we want to look a little bit closer at the oxyhemoglobin dissociation curve. This is also often referred to as the hemoglobin binding curve for oxygen. And what you can see down here at the bottom, we have the alveoli, which have the highest percentage of partial oxygen pressure, not percentage, highest amount of partial oxygen pressure. And when you follow this up, you can see that for the point E, we have almost 100% saturation of hemoglobin. Now, if we're going down here for tissue, you can see that the tissue has, because it uses the oxygen, the partial oxygen pressure is lower. And what you can see still on this sigmoid shaped curve of hemoglobin, we still find over 75%, almost like still bound to hemoglobin. This tells us two things. So while we enter the capillaries at the arterial end, we have high oxygen, still almost like at the alveoli because there's no exchange before. But then at the venual end of the tissue, we actually still have about 3/4 of our oxygen is still bound to hemoglobin. We are not emptying hemoglobin all the way out, meaning we don't deliver all the oxygen to the tissue under normal circumstances. The area now from 75 down to 0, so about 75% of the oxygen still bound to hemoglobin, is referred to the venous reserve, also referred to as oxygen reserve in our venous blood. So what we now want to look at, that this is the amount of oxygen being transported to the tissue. So we're dropping off about 25%, 1/4. Now there are ways how the protein hemoglobin, as our delivering protein for oxygen, can actually drop off more of the oxygen at the tissue. And that depends at the activity stage of the tissue. For example, temperature can have an influence, as you can see on the top graph to the right. If I increase my temperature, what happens? We're dropping more oxygen off. If you remember correctly, for example, under fever, we have a higher metabolism, so we need more oxygen to supply the oxygen to this metabolism. And as you can see, that's exactly what's happened. Suddenly we go from like 75%, we drop off down to 60% saturation level of hemoglobin, meaning we're leaving now 10% or 15% more oxygen actually at the body, which is really good. The same with pH, the hydrogen ion concentration does the same thing. If I go into more an acidic environment, which happens, as you know, with high CO2, I'm shifting my hemoglobin curve a little bit to the right, the bright red one of the two of the graphs in the bottom now. And if it would get too basic, I'm shifting it to the left. Shifting my hemoglobin saturation or binding curve to the right or to the left affects actually the amount of oxygen released, meaning it changes the affinity for hemoglobin of oxygen. So temperature shift to the right will decrease the affinity for oxygen by hemoglobin. That means it drops more oxygen off and leaves more oxygen in the tissue where it's needed. For the hydrogen ion concentration, acidity decreases the affinity for hemoglobin, and with it, what happens to the oxygen release? More oxygen is released. Alkaline, so again more basic. Oops, this area is the wrong way, I apologize. I corrected this arrow here. We increase the affinity, and that means oxygen release is lower. Stronger binding of oxygen to hemoglobin with decreasing amount of hydrogen ion present. So I just want to point out I corrected this. Please keep in mind this is my first time of taping these things, but I wanted to give it to you on Tuesday and not have you wait even longer. Now, carbon dioxide concentration also can affect my hemoglobin binding curve, and it is to the following. High carbon dioxide will also decrease the affinity for oxygen, meaning we will release more oxygen from hemoglobin. Low carbon dioxide can increase the affinity for oxygen. The same is for the presence of BPG. BPG in itself is only produced in when the body wants to do fermentation. This can also be induced or created as an intermediary in this process, also when epinephrine or thyroxine hormones are high, meaning when the body needs more energy than it can easily get. That means also we need more oxygen, so the affinity is also decreased with the presence of PBG. You can find in your book for all of these different kind of graphs showing this. So, but if you think about the conditions here, when is our body temperature increased? When is our hydrogen ion concentration increased? When is our carbon dioxide concentration increased? This all, or when do we need more PBG, or when does more PBG appear? And everything happens when we are working out, i.e., when we are hard working out, our body temperature rises. Remember, you sweat when you work out. Your hydrogen ion concentration increases, meaning your pH decreases, because what you're doing, you're creating more CO2. And remember the equation with CO2 plus water can create bicarbonate and hydrogen ions. So there you have the relationship with this. All of them give us a right shift of the curve, leaving us to a decreased affinity for hemoglobin for oxygen, allowing more oxygen to be dropped off. And let's not forget oxygen concentration in itself. Oxygen concentration in the area, i.e., for example, now in the drop-off area from the tissue, will also affect our hemoglobin binding curves. This is also referred to as the Haldane effect. So the oxygen exchange here is quickly seen. We have oxygen mainly bound to red blood cells, and then we also, as you can see here, the diffusion back. And at the bottom you find also listed these influencing parts which allow hemoglobin to release it. Why does hemoglobin release it? Under increased temperature, increased hydrogen ions, increased BPG, or increased carbon dioxide. Because as you look really closely on these, we are changing the conformation of hemoglobin, and that makes it less likely for oxygen to stay bound. And that's how we can increase the amount of oxygen we might drop off our systemic cells at a time when our systemic cells need these. So isn't that the perfect system in that manner, and at the time when we have low oxygen in the systemic cells too, i.e. during exercise. So now for the internal respiration systemic gas exchange, as we said, we still have our gradients, because inside the cells we have lower oxygen contents. They use the oxygen up. Now we are arriving with about 95 millimeter oxygen at that time. So you can see we come from the blood into the tissue cell area. For CO2, which is produced inside the cell, it wanders from the tissue cells out to the capillaries, and this gradient, just like before, is way smaller than the oxygen gradient. But again, due to the higher solubility, it still can be completed. So while we're at the venular end of the systemic capillary, we have a partial oxygen pressure from about 40 and a partial carbon dioxide pressure from about 45 being transported out of the cell. So let's look one more time now at what happens with CO2 in details. So the carbon dioxide exchange now is the loading of the carbon dioxide, and as you can see here with number 1, carbon dioxide will enter as a gas through the membrane of the red blood cells, also the red blood cells. There it combines with water, and with the help of the enzyme carbonic anhydrase, it will actually form hydrogen ion and bicarbonate. Now the bicarbonate will do again the chloride shuffle, meaning allowing chloride to enter the cell to even out the charge changes, but the bicarbonate itself will travel mainly within the plasma membrane. But now also look please here at the top at our hydrogen ions, which we free. This hydrogen ion doesn't stay free and make it more acidic necessarily directly, but what it does, they actually bind to certain groups within the hemoglobin, and that can affect now the hemoglobin binding affinity for oxygen, what we talked earlier about, the factor affecting our oxygen release at the systemic cells, and this way help to release more oxygen to this. So I hope this gave you a quick overview independent of the book. Feel free to email me if you have further questions. Otherwise, I see you all on Monday, March 31st, where we also cover this in class. Thank you.